So let's discuss assignment 3 question solutions. So in question number 1, we are asked if an inverter low. So let's take an inverter, and in an inverter, if the input voltage Vn starts dropping from VDD to VDD plus VTP, remember VTP is negative, right? And it just crosses this, the output voltage turns on in subthreshold, depletion, saturation, or linear. So this is the source, this is the gate, and just as the input voltage Vin crosses the VDD plus VTP mark, we get that VSG, which is this voltage, will increase beyond VTP. Actually, it's minus VTP. VSG is VDD, VS is VDD, VG is VDD minus VTP. So VSG will just increase beyond minus VTP. So that means it just turns on, and the output voltage, because the PMOS is just turned on, will still be around, will be close to ground. So this is like close to VDD, whereas this is really small. The VGS is really small. VSG is really small. And therefore you will see that VDD is far greater than VSG minus VTP for this sort of zone, and it will be in saturation region. So in question 3, we are given a short channel inverter with its various parameters mentioned here, and we are asked to find what the trip point is. This is a straightforward application of the formula for the trip point of a short channel inverter shown here. This is the formula, and you can see the calculations for this here. Please pause the video at this point to verify that this is in fact correct. Yeah, so in question 4, we are asked, we are given the gain of an inverter at the trip point, and we are asked what VIH is. So over here you can see the V in V out of the inverter, and the actual curve is in green, but our noise margin approximation is in pink, right? This is the noise margin approximation, and the way to construct it is to simply draw a tangent at this point Vm comma Vm, and extend the tangent until it hits VDD, and extend the tangent on the other side until it hits x-axis 0, right? The x-intercept on the 0 side is VIH, and the VDD, the x-intercept at the x-coordinate at the VDD intercept is VIL. So now the idea is that we need to find what VIH is for this problem. Now we know that this is a line. The pink is a line which has a slope of G, right? And that if we move delta Y, then we have to move delta X, which is given that delta X is equal to delta Y by G, right? Of course, now delta X is going to be VIH minus VM, and delta Y is going to be 0. Delta Y is going to be, because Y is 0 here, right? 0 minus VM, and the gain is minus 20. Right? So therefore we get VIH is equal to VM plus VM by 20, and we know that the trip point VM is VDD by 2, which is 1 volt, which is simply 1 plus 1 by 20, that's 1.05. And similarly in question 5, you can find the VIL either by getting the formula from the notes, lecture notes, or by doing it by the delta x delta y method for a line, and you will get it to be equal to 0.95. So for questions 6 to 9, we are actually given some common data about the constants involved in the current equation, and we are given 4 circuits A, B, C, and D, and we are asked to find out uh, the various quantities regarding the circuit for the different values of VIN. So in question 6, we are asked to find out what the output voltage is at VIN equal to 0. And for VIN equal to 0, of course, the current is 0. So that makes it easy. If the current is 0, then IR drop is 0. So V out is equal to VDD. So in fact, you could as well, and VDD is equal to 2 volts. So you could as well find that the only option that says V out for A is 2 volt is this. And from there itself, you can just say that this is the correct option. But of course, if you were to go ahead and find out the V out for this case, it would come out to be 1.6. And over here, since now you've upped the gate voltage, before the gate voltage was 2 volts, now the gate voltage is 3 volts, which means this NMOS will pass the VDD strongly, and therefore you get 2 volts there. And since this is an inverter with input logic 0, you'll just get output as high, and that's 2 volts there. In question 7, we are asked to find out what VOH is. Remember that VOH is the V out when Vin equal to VIH, which is 0 volt, which is input is Vin equal to VIL for an inverter, right? And that is 0 volts. So it's just the same thing as question 6. So the answer is option D. So question 8 only asks us to find out what the output voltage is at Vin equal to VDD, and I have it worked out over here for circuits A, B, C, and D. Circuit D is easy, it's just 0 volt because Vin is equal to VDD, and MOS is completely turned on, PMOS is completely turned off, and the output is pulled properly to ground. But of course, circuits A and B, A, B, and C require some calculating. So I will just go over the calculations, and you can pause the video at any point to see if it makes sense or not. Right? So that was circuit A, and then this is circuit B, where I had assumed that the NMOS on the top is in linear region, and the NMOS on the bottom, this is bottom transistor, and this is top transistor, right? Its gate voltage is VDD, whereas this guy's gate voltage is VDD minus V out, right? So I assumed that the bottom transistor is in linear region and top transistor is in saturation region. Went ahead, got the output, and if you plug this back in, you'll see that in fact the assumption was correct. And for the circuit C, I went ahead with the same assumption, but solved for the I equated both the top and bottom transistor currents to obtain one answer, which I eventually, when I plugged it back to the VDS and VGS minus VTs, found that it's the assumption itself is wrong. That is the top. If you assume that the top is in linear, the top is in saturation region and solve for it, you'll get some way out. but then you will find out that the top is actually in the linear region for that V out. So this is a contradiction, so the assumption is wrong. Then I just assumed that both the transistors are in the linear region, went ahead and solved for the V out, right? And then checked my assumption and found that it is in fact the output voltage that I got in fact matches my assumption. So, and of course circuit D is 0 volts. So in the questions 10 to 13, we are asked to find what the midpoint voltage is for the CMOS inverter with the following configurations. The midpoint voltage, you'll find out that for all four questions, the region that both the transistors is in velocity saturation, and the velocity saturated midpoint formula is shown here. So all you need to do is find out what WP and WN are, and then it's just a matter of substituting correctly for the formula, right? So I'll just go over the WP and WN. In question number 10, PMOS is of size 11, so size 11 means 11 times W min. NMOS is of size 6 means 6 times W min, and W min is of course given here. Over here we've just directly given the value of the sizes in lambda, and similarly size 5 and size 8, and the reference inverter has a size WN5 lambda, WP 10 lambda. And if you were to substitute uh, the values in the formula, you will get the following as the answers for the questions.